lovely introduction. I'm really happy to be here. It's always really fun for us to kind of get out of our research or university bubble and do these kinds of talks, educational, public based as well. So already you know that my name is Shani and I do work out of the University of Technology, Sydney. So I'm currently finishing up my PhD there, and I'm also working as casual academic and research assistant. And I do all of my work under the supervision of Dr. Micah Newland. Now, she is the Deputy Director of AFTER, which is the facility that we work at, and also Associate Professor Barbara Stewart. So today's talk, I just wanted to give a bit of an overview of the background and history of where we've come from in terms of taphonomy and what it is, why it's important that we do what we do, and why we have the facilities across the globe. Through a bit of a walk of AFTER, which is in Australia, and then go through some of the research and training that we do and the outcomes as well. Now, just a bit of a warning, there will be some images of human and animal remains at different states of decomposition throughout the presentation. So I do apologise if that does make you feel uncomfortable. So please just look away while they're on the screen as well, okay? So history lesson, where we came from in terms of taphonomy, our roots in archaeology and paleontology, and through that kind of evolution, they formed to the word taphonomy. Now, taphonomy has its roots in Greek words, so taphos meaning burial or tomb, and nomos meaning law. So together in its essence, I guess taphonomy is burial law. And what we do in taphonomy is we examine post-mortem remains, so whether or not that be human or animal, and we examine all of the changes that occur, so biological, physical, chemical, between that first point where the heart stops beating up until the remains become skeletal. Now, just a bit of a walkthrough of externally what happens during the decomposition process. It's important to kind of caveat that these 5 stages don't always occur in a linear fashion, or we might only see a few of the stages, or they might be a bit more progressed than others. And that's really just dependent on the climate, scavenging activity, if there's been a lot of rain, if it's really hot, all of that kind of stuff. So the first category that we have is our fresh remains, and that one's pretty straightforward. The individual or animal will pretty much look as it did in life. There's no external visible changes that are occurring at that point in time. But once the process starts to progress, we'll go into what's known as bloat stage. So here I have an image of one of our pigs at the facility, and it's a really typical representation of what we see for bloat. Now here you can see that there is discoloration, so it's got green and bluey discoloration. In life, this little piggy was quite pink and fleshy. And then we're also seeing a quite largely distended abdomen in that image. And that's because what happens during the fresh and then the bloat stages is all of the soft tissue inside the body, so things like the muscles and organs and all of that kind of stuff, it starts to break down and then it produces liquids and gases within the body. So these liquids and gases kind of continue to accumulate within the body and they have nowhere to go, so they do bloat the body. Following the bloat stage, at a point, there will be some purging of liquids and gases, and that's because you know, the abdomen or the limbs can no longer distend, and so they'll escape eventually. And that's where we see typically a lot of our scavenging activity. So once all of those liquids and gases are released into the environment, you'll see insects and local fauna scavenge the remains, so the soft tissues and things like that, and they'll really start to consume it. And that is known as our active decay. Now, typically in our active decay, that's where we see an increased rate of decomposition, if you like. So someone could be in the fresh or bloat stage for quite a while, but as soon as that purging occurs, because of the consumption of the soft tissue from those scavengers, progress quite quickly. And that will continue up until we get known as advanced decay. Typically at this point, we'll see some soft tissue, but mostly the hard tissue. So things like cartilage, maybe some mummified skin or epidermis, and then quite a bit of bone is exposed. So in that image there of the pig, you'll see that there are still some maggots visible, but nowhere near as what there was in the active decay. And this process will continue, so all the consumption but that's our bones. So externally, in terms of the decomposition process, but internally, there's quite a lot of biochemical changes that are occurring. And I think it's really important to kind of understand where those progressions occur so that you can relate them to the external visible changes. So during our early postmortem period, so when something looks fresh, generally we can have a look at three different things, and those are the three mortises. So rigor mortis is the most commonly known one, and that's just generally when you get the stiffening of the joints and the limbs. But alga mortis is another one that we look at, and for forensic practitioners, it's a little bit more useful because they actually have a regression calculation where in some cases they can use alga mortis to kind of estimate how long someone's been dead for. Now, the phenomena behind alga mortis is that when someone dies, say we're about 36.5 degrees in life, the environment that we are in, if it's cold, for example, our body temperature is likely to decrease to that outside temperature and via a really warm climate. And based on mathematics and that regression calculation, they can someone's been dead for according to that temperature. So that's where alga mortis is quite useful. And the other one that we have is liver mortis, and that is just because once the heart stops beating, obviously nothing is pumping around the blood in the body, and so we see this accumulation or settling of blood. And in the image here, we have an individual who was in a supine position, so laying with their back on the posterior surface, and you can see that they're in the area that was in contact with the surface, the blood has been pushed away and it settles like that. So they'll be like that until they start to decompose. Another interesting thing that we don't always see during those early postmortem changes, but I included it here because it's quite interesting for some people, but if in more wet or moist environments, the epidermis will start to slip off. So here we have a perfect example of what's known as skin slippage. And that's just where that outer layer of skin will generally fall off. Interestingly, they can still try and get some prints off that as well if they were looking at it in a forensic case. So moving on from those early postmortem changes where we get more into that bloat and active decay, we see autolysis and putrefaction. Autolysis is where all the cells within our body, they start to explode. They're destroyed by enzymes within the body. And that's when those processes really start to speed up during active decay. And this is an example, of what we see. This is known as skin marbling, and that's because those cells have been destroyed inside the body, and you get to see a lot of discoloration as well. So you can see that from the outside. Then that moves into putrefaction, which is where I do a lot of my work. So that's where the macromolecules in the body break down. So think like your lipids, your proteins. That's generally where a lot of the decomposition chemists like myself do a lot of their research. So I'm looking at the breakdown of lipids, for example. And the reason that we do that is because in theory, if we understand the way that those macromolecules break down in decomposition, it's likely that we can estimate how long someone has been dead for based on those patterns. So working backwards, I guess. And then we get into our liquefaction, which is where we've bloated, we've gone into active decay, and then all of those liquids are purging from the body. And that's because all of the soft tissue has disintegrated. And that's when we move on to our skeletonization. In some cases, if remains have been outside or left on the soil surface for quite a length of time, you will see some chemical and physical weathering where you get those really nice white and clean bones. So now that we've looked at the external and internal aspects of what taphonomy is and what we look at, I wanted to give it a bit more context as to why we do that in forensics. And so if we fully understand how human bodies decompose in different environments under different conditions, it can really help us with the search and location of remains. It can really help us establish the post-mortem interval, so how long has someone been dead for? And then it can really help us in terms of developing new research methods for identification of remains as well. So that's kind of where in forensics that sits in context of the taphonomic factors. Now, this is one of my favorite cases that I always like to do at these kinds of talks, because I feel like if you hadn't already understood why it's important what we do, this case really is the last nail in the coffin, if you will. So 1970s, a case over in the United States came to light, and there were some remains that were found on top of the grave of a Civil War hero. His name was Colonel Shine. And so the police had called through a forensic expert. At the time, he was a forensic anthropologist, and they wanted him to kind of figure out whose remains are these and where did they come from. Now, Dr. William Bass, who was the expert, he estimated that the age of the remains were 26 to 29 years old, which was correct, that the remains were male, that they were Caucasian, 5'11", and around 175 pounds. But unfortunately, he had estimated at the time since death, so those remains had been dead for only around 2 to 6 months, when in fact they were actually the remains of the Civil War hero. So he'd been dead for about 113 years. And the reason that he got that estimation so wrong, at that point, we didn't really understand how human bodies decomposed, and we didn't really understand how they decomposed in different environments. So unfortunately, Dr. Bass, it's not that it's his fault, there just wasn't enough knowledge out there, and we didn't have the facilities to actually study this. But he didn't consider the fact that these remains had actually been embalmed prior to being buried, that the remains were closed, they were in a coffin, they were buried. So all of those factors really impact on the preservation of the remains. And so Dr. Bass, as a good scientist does, he actually created our first body farm or taphonomic facility. And that was over in the United States in Tennessee in the 1980s. So, you know, being 2022 now, we're still quite in its infancy, but the work that we're doing now is a bit of an exponential curve where we've come a long way since then now. But the term body farm actually got coined because Patricia Cornwell was really interested in this facility, and so she went out there and she spoke to Dr. Bass, and she kind of got a bit of a walkthrough, and she wrote her book known as The Body Farm. So that's kind of where that term came from. We as researchers, we prefer not to use that term, but we refer to them as taphonomic facilities, so just out of interest. Now, one point of contention is, well, okay, we have a facility over in the United States where we can do whole human cadaver research for decomposition focus, but why do we need them in different places of the world? And the main reason for that is that climate, vegetation, scavengers, so insects and fauna, all of that are one of the biggest drivers in decomposition, okay? So at current, we have around 10 facilities across the globe, I believe. So we've got a few in the United States, we've got some in Europe, and then we have the only one in the south in Sydney, Australia. Now, a comparison just of the climate between the United States and Australia, for example, they're completely different. So the issue there is when we're trying to translate data obtained from United States facilities, for example, to Australian casework. So you can see that it's not a and same thing goes when we look at the vegetation, for example. So that's another key driver of decomposition. And again, once we try to translate data from another continent to ours here in Australia, we come across quite a lot of error. And so we realized, well, we need to do something about that. And we actually opened up our first facility known as AFTA in 2016. So AFTA actually stands for the Australian Facility for Taphonomic Experimental Research. It is a bit of a mouthful, so we do just refer to it as AFTA. And it is an open eucalyptus woodland at the base of the Blue Mountains, and it is owned primarily by University of Technology Sydney, but it's also quite a collaborative and multi-jurisdictional facility. And this facility allows us to study whole human decomposition in a really controlled, really secure environment. Now, I mentioned that it is multi-jurisdictional, and what I mean by that is that we don't just work with researchers at UTS, we work with researchers all over Australia universities, but more importantly, I think, you know, one of the biggest things that we want to do at the facility is have quite a big impact in terms of the community and the reach that we have for the outcomes. And we generally get that because we work with industry personnel. So the Australian Federal Police, military police, we even work with the Australian Museum and the Victorian Institute of Forensic Medicine. And again, that's because we really want to focus what we do out of the facility to have that big impact on the community so that we can really aid in forensic casework, for example. Now, a bit of a walkthrough looks like. It is really simple. We are pretty much only got the one structure on site, which is what we were looking at here. And it does have a really simple toilet and shower for us researchers. It is pretty dirty work sometimes what we do. And then we've got a little kitchenette for us to have tea, coffee, heat up our food. And then there's also an area for us to store all of our chemicals and samples and all of that kind of stuff. You will also notice that we've got quite large security fence line around the perimeter of the facility. And unlike in a prison, it's not to keep people from getting out, but it is to protect the dignity and secure the location of the donors as well, so that nobody, unless they're authorized personnel, can get into the facility. Now, this is an example of what the rest of the site looks like. And it's pretty rural. Now, we keep it like this because we do really want to mimic what we see in casework. So everything that we have out there, you know, we might mow the lawn in certain areas or anything like that to walk through, but everything else that we're looking at is pretty much depicted in this picture. The reason that we have these facilities is so